Good morning, everyone. I'm Professor Lin from Department of Systems and Naval Mechatronic Engineering, Naval National Cheng University. It's really my pleasure to attend the second International BigOCEAN Metarence and share our lab's research with you by the topic image-based visual servo control of autonomous underwater vehicle applying deep reinforcement learning. Well, I would like to say exploring the oceans and delving into the depths of our minds are inherently intertwined journey of discovery and understanding. Just as the vast expanses of the ocean host mysteries waiting to be uncovered, our minds harbor untapped potential and unexplored territories of thought and creativity. By immersing ourselves in the exploration of both realms, we gain profound insights into the complexity of our worlds and ourselves. You may ask why we learn ocean engineering. My advisor, Professor Lorna Young at UC Berkeley, ever told me that the marine engineers must remember three digits, 7, 8, and 9. 7 means that the ocean occupies almost 70% area on Earth. 8 means 80% population of human beings live nearby coastal areas. And 9 means 90% economy activities are dependent on the ocean. Therefore, there are still lots of opportunities that are waiting for our exploration. So, how is the application in ocean engineering? I think that there should be an animation, but I cannot see anything. So maybe that's a technical problem. Well, it's well known that the offshore wind industry is growing up very fast, especially in Taiwan. So when the offshore wind farm enters the phase of operation and the maintenance, we cannot rely on conventional divers for long-term and dangerous inspection missions. Fortunately, the AUV can be a high-efficient alternative solution to this kind of high-risk and routine inspection missions. Well, there should be animation. Cannot see it move. So, but it's okay. And then you may be interested in what we can do in ocean engineering. The researchers in our lab, a marine technology and engineering laboratory, mainly belong to 4 categories. They are offshore wind engineering, towing task, autonomous underwater vehicle, and intelligence systems. Because of limited presentation time, I will briefly show you the abstract for each topic and the relevant projects and the publications. If you have any interest in each topic or collaboration, please don't hesitate to let me know. Well, the contents of this lecture are briefly presented in this page. First, I will show you a review of underwater vehicles, and then I will introduce how we design our AUV. The development process of applying IBVS to our AUV will also be presented. Finally, I will talk about the ongoing and the future research in our lab. Well, AUV come into 2 main types, just as you see in this page, hovering and the torpedo. Hovering types are designed to remain stationary in water, while torpedo types are built for swift navigation. On the other hand, ROV rely on an umbilical cable for power and operation. These vehicles find applications in various industries such as oil and gas, oceanography research, and mine mode operation. In scientific research, underwater vehicles are equipped with sensors to conduct tasks such as monitoring water quality, studying aquatic organisms, and observing marine physics phenomena. Meanwhile, for underwater structure inspection purposes, these vehicles are utilized to inspect ship hull appendages as well as dams and bridges. Deep sea exploration has been greatly advanced by the development of autonomous benthic explorers (ABE) by the U.S. Woods Hole Oceanography Research Institute in 1995. The ABE utilized sonar positioning to navigate the deep sea and is capable of remaining on the ocean floor for extended periods, significantly enhancing our ability to study the depths of the sea. During its disaster investigations, the AUV Rumors 6000 play a crucial role in examining the crash site of Air France Flight 447. Utilizing side scan sonar technology, ABYSS located significant wreckage, including the first wings, engines, and the landing gear. Additionally, working in tandem with American ROV, the flight recorder of Air France 447 was successfully recovered during the initial dive, highlighting the effectiveness of autonomous underwater vehicles in disaster recovery efforts. In industry applications, AUV are employed for various tasks, such as surveying underwater power cables, locating underwater mineral deposits, and mapping the seabed. For example, the Sea Surveyor 6 is utilized for these purposes. Furthermore, a new survey mode has emerged where Geodetic Offshore Surveys Limited utilize stream-body AUV to conduct surveys on existing or new underwater pipelines in the West African region. In submarine simulation, AUV find application in the fabrication of semi-autonomous free-running models, such as the BB2. These models enable researchers to simulate and study the behavior of submarines in various underwater conditions, aiding in the development and the testing of submarine technologies and strategy. Okay. For the design of AUV, accurately estimating the hydrodynamic coefficients and the resistance will have a significant effect on their maneuvering performance. Therefore, an innovative and efficient experimental procedure is established to analyze the maneuvering derivative of a half-scale submarine body, sub-off, in the horizontal plane for 4 different types, including bare hull with sail, bare hull with rudders, and bare hull with appendages, by conducting the so-called planar motion mechanism (PMM) experiments in our towing tank, 176 meter times 8 meter times 4 meters of NCKU. The PMM experiments comprise both static tasks, for example, the oblique towing task and the dynamic task. And it's worth to mention that the maneuvering derivative derived from the PMM test are in good agreement with the result published by the DTRC. and to improve the propeller performances. This study simulated Q7 brand Hsien E1690 propeller in open water conditions using a large eddy simulation, abbreviated as a LES model with dynamic mesh technology. Two-phase flow was generated using a volume of fluid, abbreviated as the VOF, measured to adjust free surface effect, and a user-defined function controller propeller motion. Validation against open water tests in an ACKU towing tank show high success rates with total uncertainties below 6%. Grid and time-step sensitivity analysis were performed, and the results are used to analyze hydrodynamic performance and the flow structures around the propeller. Findings indicated that propeller with charge consistently outperform single propellers in predicting thrust, coefficient, and efficiency, while single propellers show slightly better torque coefficient predictions. Well, after completing the aforementioned constraint model test, free-running tests of a vehicle will be conducted. The key capability of this research is to develop the submarine free-running model, SFRM, that can be used to investigate the extreme maneuvers for comparing safe operation envelopes, SOE. The free-running submarine model provides the ability to evaluate scenarios and environments that reflect the operational requirements of submarine under consideration. To determine performance characteristics, undertake design trade-off, identify constraints, and to compare alternative designs. It will be applicable to the in-service and the design stages of all submarine programs and provide advice and guidance to the Navy regarding key capabilities of submarine maneuvering and control. Well, let's talk about the design of our AUV. Sorry about it, it's a little bit late. Well, okay. The AUV can be considered as a system that integrates various sensors, while also needing to examine whether its functionality meets mission requirements. Just as we know, the accuracy of navigation and the localization for AUV in underwater environments is particularly challenging due to the rapid attenuation of global precision systems and the radio frequency signals. Therefore, this research aims to provide a new alternative solution of AUV for positioning and exploration of unknown underwater environments by using vision-based sensors to develop a two-dimensional map and three-dimensional objects. After function customization, our AUV can be adopted in the fields of entertainment, aquaculture, inspection of ship hull and auxiliary facilities, underwater securities of ports, mine countermeasures, unexploited oceans, and applications in marine science, marine resource protection, and underwater rescue. Well, we have already known that the hydrodynamic analysis dominates the maneuvering performance of the AUV. But what if we don't have reliable experimental facilities like the PMM? The alternative is to establish a dynamic mesh model based on the horizontal planar motion mechanism HPMM test and provides a comprehensive database of hydrodynamic coefficients for the AUV numerically and experimentally. A series of HPMN tests in NCKU towing tank validated the simulation results. The dynamic mesh model can be performed on oscillation motions of the yaw mode, the pitch mode, and the low mode by adding a series of comprehensive user-defined functions. Since most numerical results are reasonably in good agreement with the experimental data, applying the proposed dynamic mesh model in the simulation of an HPMN test in a towing tank can be demonstrated. Let's talk about the maneuvering test of our AUV. Well, in the following maneuvering test, we developed an experimental-based adaptive fuzzy controller for the diving control system, let's so-called a DCS, of autonomous underwater vehicle to ensure high stability and rapid integration. The DCS we developed is designed with the depth sensor and an attitude and the heading reference system, AHRS, to sense the attitude vector and the current depth of AUV in real time as the control inputs of attitude closed loop and calculate yaw and pitch controls of AUV. Consequently, the proposed adaptive fuzzy control DCS is a model-free design that resolves the problem of depth keeping and the attitude stability controls of AUV with unknown hydrodynamic coefficients, rudder dynamics, and the time-varying external forces. And then I will talk about IBVS control. And the IBVS control is an image-based visual servoing control. The IBVS technique establishes a closed-loop control system within a 2D image space. It achieves this by extracting features from the visual information of the observed object, computing the error relative to the desired features, and formulating a control law based on this error. In eye-in-hand robotic setup, just as you see on the bottom left side, the camera is positioned on the robot's end effector, enabling it to provide visual feedback from its perspective, particularly useful for tasks like the object manipulation and the navigation. On the other hand, in the so-called eye-to-hand configurations, the camera or vision system is mounted separately from the robotic manipulator, offering visual feedback to ensure precise control during manipulation tasks. Well, do you hear me? I think it's a little bit late. Okay. Well, let's talk about application. The light source identification is the first technology we developed in the IBVS control of our AUV. In this research, underwater recognition technology and the fuzzy control system were adopted to adjust the attitude and the revolution speed of a self-developed autonomous underwater vehicle. An underwater lighting box was towed by a carriage at low speed. Unfortunately, I think all of you cannot see anything in the animation. I don't know what happened, but it should be a video and showing the experimental procedure, but I will try to explain it in detail. Well, by adding real-time contour approximation and the circle fitting algorithm to the image processing procedure, the relationship between the AUV and the underwater lighting box was calculated. The both rudder plane angles and the propeller revolution speed were determined after the size and the location of the lighting box was measured in the image. Eventually, AUV performance with the visual recognition control was verified by controlling the target object in the image center during passage. The second IPVS control technology is color identification. So we propose the development of an underwater object tracking control system through an image processing technique. The image processing technique includes color space conversion, target and background separation with finalization, noise removal with image filters, and the image morphology. After the image information is obtained for underwater object, the image area and the coordinates are further adopted as the input value of a fuzzy logic controller to calculate the rudder angle of servo motor. And the propeller revolution speed is defined using the image information. The aforementioned experiments were all conducted in a stability water tank. Subsequently, the fuzzy logic controller FLC was combined with an extended carbon filter EKF for further dynamic experiments in a towing tank. Specifically, the EKF predicts new coordinates according to the original coordinates of an object to resolve data insufficiency. Consequently, several tests were analyzed to observe the changes in the rudder angles and the sensitivity of the propeller revolution speed. And then let's talk about the deep learning. The deep learning is a machine learning technique that utilizes multi-layer neural networks to mimic the way of human brain processes information, enabling automatic feature learning and the complex pattern recognition and prediction. Therefore, we aim to develop a fuzzy-based visual intelligence guidance system, let's say VIGS, that executes missions involving the identification and the checking of underwater target objects for an autonomous underwater vehicle. The characteristic of the VIGS is to immediately capture continuous real-time images from the board to calculate and identify visual information concerning the AUV's surroundings. By mapping the target's information in the AUV visual coordinate system onto the Earth's physical coordinate system, the relationships of a corresponding distance and the azimut between the target and the AUV were defined. Eventually, this information was used to calculate the control parameters of the AUV's moving speed and the head angle, completing a visual motion control framework. Well, and then let's talk about deep reinforcement learning. The deep reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment receiving feedback in the form of rewards or penalties, and utilizing deep neural networks to approximate complex decision-making processes. Due to this advantage, our purpose is to design and realize an intelligent underwater recognition system of autonomous underwater vehicle for identifying and checking underwater objects. The Intelligent Underwater Recognition System, IURS, can predict a depth map by using the stereo matching approach based on semi-global block matching, SGBM, and then integrate with the Deep Q network, DQN, based on deep reinforcement learning to make the agent concentrate on the target in the disparity map we developed. After acquiring the depth information of the target, the region of interest, abbreviated as ROI, generated by the faster RCNN, would be used for controlling the rudders and the propeller of the AUV in the object checking test. All right. Let's talk about the DRL, path following control. We have already known the function of deep reinforcement learning, but what is the path following control? Well, the path following control, simply speaking, refers to a control strategy where a system such as a vehicle or robot autonomously navigates along a predefined path or trajectory. And in this research, we present our experimental results and the achievement for this mission-oriented project with Academia Sinica in Taiwan. Firstly, we show our research contributions on numerical simulation for maneuvering control of an autonomous underwater vehicle by combining a deep reinforcement learning technique, Q-learning, and an adaptive neural fuzzy inference system, NFIS controller. Subsequently, we present our research contributions on applying the deep reinforcement learning controller to the refinement of AUV's path following control in wave. Okay. Well, let's talk about ongoing and the future research in our lab. Basically, it covers the topic as follows: launch and the recovery system of the AUV. And the second one is a marine heterogeneous integration system. And the final one is a marine digital twin system. Okay. The first ongoing research I show you is a launch and a recovery system of AUV. For this kind of the system, we proposed the docking control system of an autonomous underwater vehicle, combine intelligent object recognition and the deep reinforcement learning. We work on this project with the MTIC. I think Professor Pan ever visited this research center last year. So right now we are conducting this research with them and to find out the so-called inspection map in our offshore wind farm. Well, basically, this study introduces a visual-based docking system, VDS, that integrates a visual navigation method and intelligent object recognition technique, and a deep reinforcement learning method. A variable information dock, let's say VID, has been comprehensively tested using an AUV with multi-sensor integration. It transformed the highly coupled nonlinear systems of the AUV into a visual motion control system capable of a real-time perception, analysis, and environmental data processing. The VDS experiments were conducted in a toy tank in NCKU. The data suggests that the VDS offers reportability, controllability, and high reliability as a platform for verifying visual navigation control methods. The second research topic is the marine heterogeneous integration system. We are now working on the project simulation of a 6 degrees of freedom motion response of an unmanned surface vehicle and development of an automatic control system with our government, the Department of Energy. Basically, it covers the fields as follows. Development. The first one is the development of a launch and recovery system for drones and AUV. This focuses on creating launch and recovery system specifically designed for drones and autonomous underwater vehicles. These systems are engineered to facilitate operations in various conditions, including both station keeping and the mobile scenarios alongside unmanned surface vehicles. The second one is 3D stream motion equations. These areas involve the formulation and the analysis of equations that describe the motion of ships in three-dimensional space. By understanding and modeling these motions, every researcher can enhance the design and the operation of marine vessels, improving their stability, maneuverability, and performance in diverse environments. The second research branch in this project is deep reinforcement learning control algorithm. Here, the focus relies on the development and the implementation of advanced control algorithms based on deep reinforcement learning techniques. These algorithms enable autonomous systems to learn and adapt their behavior in complex and dynamic environments, leading to more efficient and intelligent control strategies for marine applications. The fourth research branch is the development of Python embedded system. This pertains to the utilization of the Python programming language for embedded systems within marine technology. Python's versatility and ease of use make it an ideal choice for developing embedded software solutions that power various components of marine systems, from onboard controllers to data processing units, enhancing their functionality and interoperability. Finally, let's talk about the marine digital twin system. Originally, you are supposed to see the training procedure of this marine digital twin system, but I think everything stops. The integration of a marine digital twin system with AUV technology presents a groundbreaking approach to enhancing docking procedures. This kind of technology is very important for AUV because when the AUV enters the dock device, it usually faces the dangerous situation. That's the motivation of this technology. By employing advanced digital chain models of marine environments, coupled with real-time data from AUV, docking maneuvers can be optimized by efficiency and safety. The synergy enables precise navigation and alignment during docking, mitigating risk, and ensuring seamless operations in challenging maritime conditions. The marine digital chain system serves as virtual replica of the docking environment, allowing AUV to simulate and execute docking procedures with unparalleled accuracy and reliability. This innovative integration marks a significant advancement in autonomous marine operations, paving the way for enhanced autonomy and productivity in maritime industry. Well, the speaker would like to thank for the invitation from Professor Pan, Jeju National University. And thanks for your listening and attention. If you have any question or comment, please don't hesitate to let me know. Thank you. Thank you so much.